Hey everyone, my name is Peter Hughes. I work for a company called Push Technology, and we do real-time data out across the internet. So, what does real-time actually mean? It means quite a lot of events. We're seeing a massive rise in sort of quote-unquote real-time data, and it's increasing as more and more applications start trying to move stuff that would typically be within the data center, like contained in Kafka, out towards actual user-facing applications. So it can be like a fire hose. You can think of real-time as just massive streams of data, Twitter's kind of feed API. You have stock prices for trading applications. This is all a centralized source of data that needs to be distributed out to potentially hundreds or millions of concurrent users. But real-time can also be more user-specific. It can be more about the latency so that when something does change, say your update on your Amazon order, that gets notified to you immediately. So real-time in the context of sort of the web and applications is really a conversation around immediacy and about volume. And of course, the internet is its own unique thing. So designing APIs when you're inside the data center, you have a lot of guarantees that come with it. You have kind of known connections. You can depend on the hardware that's available to you. Or in the cloud, obviously, then it's all virtualized. With the public internet, you really need to think about things like geography and device types. Egress costs can be really high. If anyone's tried to move a large amount of data out of AWS, you realize it costs a lot more than it does to get it in. Connectivity really is not dependable. Someone can be connected in on a 5G network and everything's doing great, but they could also be in the middle of nowhere with a 2G connection or a satellite connection. You want to be able to provide the same experience, the same real-time applications, regardless of where they are, because you can't control that. And of course, there's always more connections, there's always more data. Any solution that you build to accommodate this needs to be able to handle not just the current volume, but next year's volume, the next 5 years. So we have some good solutions today for moving data out across the internet. We've got REST and polling. It works pretty well. We've got very mature solutions. Why don't we just add more servers? First problem is polling. As an architectural methodology for collecting data and moving it from some API layer to your client, it carries with it an enormous amount of overhead that when you're dealing with less frequent data access doesn't really matter, but at scale and at high frequency really starts to add up. Every connection that you make, every request that's sent from a client to a server has to have things like TLS, stripping and overhead. You need to parse the various HTTP headers. You need to actually inspect the body of the request and respond appropriately. There's also the lack of immediacy that comes with polling. If any of you guys work with Java, you may have heard of someone called Gil Tene. He has this term called coordinated emission, which is a really interesting way of thinking about latency, where the latency that we may usually think about would be from the client side, how long it takes from sending a request until we get a response. But the overall latency that we should really be caring about is how long from the data that we care about being changed on the back end to the client actually knowing about that change. In a polling model, we're basically at the mercy of every client deciding when to ask if anything's changed. And of course, as the talk in the previous session mentioned, the whole "are we there yet" issue. Because we're relying on clients being the ones responsible for when to ask for more data, even if nothing's actually changed, we're still incurring the cost of every single request that comes in. And even then, the changes might be minor, but we've paid the bandwidth and the processing overhead of all the subsequent and requests that came in before then. And this might not seem like a lot when it's just one client and one resource, but you start looking at the amount of resources that any given application might be requesting, and how many requests that you'd actually need for that to be considered real-time. And then you scale it up by the number of users that you have concurrently, you start realizing that a polling model, when you're trying to do a real-time application, is either going to become out of date because you're restricting that polling too much, or you're going to flood your systems with unnecessary, redundant requests. But the biggest issue with polling, at least as we see it, is that it fundamentally puts the complexity of getting data onto the consumer side. It's the clients that need to handle things like initiating each request. They need to know precisely what resource endpoints to ask for data from. They need to be able to handle retries and backoffs. That's a lot of additional work that we kind of just say is par for the course. If you want to do polling, that's what you have to deal with. But it doesn't have to be that way. So if we're mostly dealing with requests, which is a kind of a synchronous interaction pattern, real-time more naturally fits in towards streaming, an async pattern where you have a long-lived stream and data can then be pushed from either side as and when it's needed. So with a stream-oriented model, instead of the client having to continually ask for when something's changed, the server is responsible for being able to just tell every interested consumer when something they should know about has happened. And that maps really naturally to, say, an event streaming model, so kind of Kafka-like. But you could also think about that in terms of an event-driven database. Firebase, for instance, providing push notifications whenever something in the document model has been changed. And what you find when you move to a streaming model, too, is that the complexity of the interactions now falls on the servers. It becomes part of the API layer to handle some of the complexity that previously would have been handled by the client. So just to take a look quickly at how we do streaming on the web, there's a whole bunch of options. WebSockets, WebRTC, server-sent events. I'm not going to suggest that you should necessarily pick any particular one because it's going to vary depending on your use case, your requirements. I'm personally biased towards WebSockets. They're bidirectional, supported in pretty much every browser. They allow you to send binary data. But whichever makes the most sense, they all essentially offer streaming primitives for web and mobile. So we just add WebSockets, right? We just get our API gateways, put in a new transport, and we're done. Doesn't work. The problem, of course, is REST. So when we're dealing with REST APIs, or REST-ish, because most of us don't really do it properly, we have to deal with the fundamental fact that REST is stateless. And this is an inherent property that emerges from the fact that it's based on HTTP requests. When you have a request and response model, each request carries with it all of the information that you need to know in order to process it. Every request essentially is a standalone blob of data that tells you what resource you want to access, your authentication context, any payload if necessary. When we're looking at streams, though, we only send that sort of data once when we initiate the connection. Everything after that is assumed to be resolved within the context of that original stream, which means that we, as developers and maintainers of the server, need to remember that state. We can't rely on it just being provided to us at the point of request. And one of the major implications this has is scaling. In a request-response model, it's real simple to scale up. You have your load balancers, you have your API caches, you just add more servers, give or take a few minor details, and it usually works pretty well. When you're scaling with streams, you have to rethink what scaling actually means. Caches don't really make sense with a stream because it's a set of changing events, and it's long-lived and persistent. And for each connection, we have to maintain a queue of all the messages that we want to push out over the network. We need to remember that security context, which means now things like available memory on each API server becomes important. It means that we need to start thinking about persistence. So streaming gives us the kind of primitives that we need in order to truly deliver real-time in an efficient way, in a way that kind of avoids some of the pitfalls that request response has. But it also means that we now need to start thinking a lot more about the kind of details that come into scaling that previously we had sort of considered solved. And of course, WebSockets are really just a transport. They give you a pipe that you can push data down, but developers don't want to just deal with a single message queue. They want higher level interactions. So one of the ones that I think kind of works quite well is PubSub. It's a messaging paradigm that operates very similar to REST in the sense that it provides ways to interact with different resources and coordinate between producers and consumers of data quite reasonably. And yeah, there's a logical mapping between REST and PubSub concepts. And there's lots of products that perform exactly this really well. The ability to connect in over WebSockets or some other transport, subscribe to topics, and then get updates as and when they happen. That could be a real-time stream that's constantly flowing out to you, or it could be subscribing to changes on a particular data model. But again, PubSub brings more complications. We now have to think about persisting subscriptions. We have a stream, it can subscribe to particular topics to let us know what data it wants to receive. We need to remember that. That's even more state. And when you're dealing with a real-world production system where you have multiple edge servers, you probably want to have that state distributed. So suddenly, we're dealing with a quite complex distributed state model that previously we never had to consider. And PubSub also really doesn't answer quite a lot of the questions that we as an industry have already answered for REST. Things like security, documentation, even monetization are all issues that are pretty much solved for in REST. Again, give or take a few minor details. But in sort of the PubSub world, in the event streaming world for web, we need to be able to answer these same points to really deliver value as businesses. So this is the part where I start talking a bit about our experiences as a company and the sort of customer use cases that we've tried to solve for. This is just one potential way of extending something like PubSub. But I think the general kind of view is that PubSub isn't sufficient for most kind of real-world production applications. It's a great start, and obviously there's GraphQL, gRPC for other types of use cases, but from what we've observed, there's a couple of things that really need to be answered for customers in order to adopt a true real-time kind of application. So the first thing is security. When you move to a streaming model, the security context kind of changes in interesting ways. You have, obviously, the need to authenticate at the point of the initial connection, which is an HTTP upgrade request in the case of WebSockets. So that's TLS, that's sort of security as we normally handle it. But everything after that is done in the context of that stream. These aren't HTTP requests that we can use our existing kind of security systems for. So you need to parse every message that comes along this stream and handle it appropriately. That can be subscription requests, publication requests. You need to think about how client applications need to re-authenticate, generate new tokens in the middle of a stream, which of course is a long-lived context that exists both on the server and the client side. And you need to have a way of notifying clients in the context of that stream if any security changes have occurred on the server side. Has that client become deauthorized for a particular access, a particular resource that they were previously allowed to access? The other thing that's kind of interesting is RPC type interactions actually turn out to be pretty useful for developers. Imagine an Uber-style app where you have a real-time stream that's showing you where your driver's location is or where available cars are. But you also need to have a button that you can click to say, place my order. That's more of an RPC or request response type interaction. And you can choose to do that through different mechanisms. You could have a separate streaming transport and a separate transport for request response, but now you have two different locations in your application architecture that you need to apply security, rate limiting, quality of service to. But with a streaming sort of system, you can replicate request response really easily. As long as you have some shared identifying context, some ID on the client side that it can attach to that message, and then when your backend system responds, it carries that same context. Your client can resolve that and then present that up as a traditional RPC type interaction. You have to deal with things like persistence of that context if you want reliable messaging, but this still works really well for building up applications that have multiple modes of interaction. Querying resources is an interesting one. I think, given the number of talks or times that GraphQL has been mentioned over the past couple of days, it's something that people are really starting to think more heavily about. Obviously, with GraphQL, you submit a subscription or a live query, and then changes to the data model are presented down to you. If you're running in a pub/sub model, how do you achieve similar things? How do you parameterize your subscriptions to topics? Does a topic represent a stream of related events, or do you have one topic per resource? That can have implications in terms of the resources that your backend requires, or the complexity on the client side of how to parse and understand the responses that it gets down. Another interesting idea for pub/sub that basically can be stolen from Kafka is having an event history for streams. Topics usually are just a stateless channel, but what if you could remember past events? Your API layer then becomes almost like a cache. And of course, if you've got a cache, then you can start doing things like looking at what's changed between messages. If you consider that most sort of data messages that come along are JSON objects where at the very least the keys remain the same, even if the values change, you can optimize that by looking at the difference and only transmitting that down to clients. We do this with our technology, and we've seen reductions of bandwidth up to 97% compared to REST when you start actually looking at doing deltas. So to wrap up, what does this all mean? You have more data, and we have more problems with real time, but we also have more opportunities. I think that we have to come to terms with the fact that state is necessary, and current approaches aren't really working out. But we're going to get to a point where real time becomes everywhere. We become more efficient, more extensible, and we're going to be able to do an awful lot more with real-time applications. Thanks.